Hello, Lab Rats. This is your Lesson 19, Mechanical Waves and Sound. You're going to want to have access to the YouTube videos linked in your class participation assignment. Those videos are going to be watched in the order in which they are numbered in that assignment. Those are the videos that I would typically play within a slideshow. It might be easiest if you go ahead and open each of those links in a separate tab and have the videos pause so you can toggle back and forth between this lesson slides and the videos as we come to them. So first we're going to discuss the behavior of waves. When we come to one of these little boxes, I'm going to pause for a beat to give you a chance to think about the answer, and then we'll move on. So for this first one, reflection occurs when waves bounce off a surface that they cannot pass through. Reflection does not change the speed or frequency of a wave, but the wave can be flipped upside down. Refraction is the bending of a wave as it enters a new medium at an angle. When a wave enters a medium at an angle, refraction occurs because one side of the wave moves more slowly than the other side. Diffraction is the bending of a wave as it enters a new medium at an angle. A wave diffracts more if its wavelength is large compared to the size of an opening or an obstacle. Waves can experience interference, which occurs when two or more waves overlap. You have different types of interference. The first is constructive interference, which is when two or more waves combine to produce a wave with a larger displacement. And then you also have destructive interference, which occurs when two or more waves combine to produce a wave with a smaller displacement. You can think of this like those parachutes the little kids play with. When everybody goes up and down with the parachute at the same time, and you get a really big displacement going up and down from the equilibrium, everybody's moving together. That is an example of constructive interference. When they throw the balls out on the parachute and they have everybody shake it like crazy, that's an example of destructive interference. Now you can also have standing waves. A standing wave is a wave that appears to stay in one place and does not seem to move through a medium. You have nodes, which are the point on a standing wave that has no displacement from the rest position or equilibrium, and you have antinodes, which are the points on a crest or a trough that appear midway between two nodes. Standing wave forms only half of a wavelength or a multiple of a half of a wavelength that fits exactly into the length of a vibrating cord. Resonance. Most objects have a natural frequency at which their particles naturally vibrate. This is called a resonant frequency. Resonance occurs when vibrations traveling through the object match its natural frequency. And you can think of resonance, for example, when you're pushing a small child on a swing. There's a sweet spot in the back swing where if you push the swing and the child on the swing, the child will go higher and higher each time. That's because you are matching the resonant frequency of that particular swing. Now, if you were to like step in the middle of the back swing or the front swing and then add a push where it didn't really belong, that's more like you're getting, you're not working with the resonance, so you're getting a sort of a deconstructing of the wave. So now I would like you to watch your first video, which is the Tacoma Narrows Bridge collapse. And what happened here was the resonant frequency of the bridge just so happened to match the resonant frequency, or the frequency produced of the wind passing by. And so you can see what happens to the bridge there in the title, but go ahead and watch that old newsreel video. Now we'll discuss sound and hearing. Properties of sound waves. Sound waves are longitudinal waves. Many behaviors of sound can be explained using a few properties such as speed, intensity, loudness, and pitch. Speed. So the speed of a sound wave is going to vary greatly by the medium through which the wave is passing. I now want you to watch video number 2, the speed of sound in different substances. Intensity. is the rate at which a wave's energy flows through a given area. Now, a decibel is the unit for sound intensity. It equals 1/10 of a bell, named for Alexander Graham Bell, based on the unit of power in the Bell system, which deals with telephony, telephones. This is one of those weird units where decibel is pretty much always what we use as a base, even though bell is really the base because a decibel is 1/10 of a bell. So even if something is 10 decibels, it's really just a bell, but we say 10 decibels. Loudness is the physical response to intensity of sound modified by physical factors. So here's a decibel scale, and as you can see right here, where there's the first little icon there for breathing, breathing is shown as 10 decibels, which makes it a bell, but we never say that. So you can get things as quiet as 10 decibels to, like, for example, here the firework is 140 decibels. Frequency and pitch. Pitch is the frequency of sound as you perceive it. Ultrasound is used in a variety of applications, including sonar and ultrasonic imaging. Sonar is a technique for determining the distance of an object in water, and it's a type of acoustic location. Then we have the Doppler effect, which, as you know, applies to light as well as sound, because we discussed it back at the very beginning of this year. The Doppler effect is a change in sound frequency caused by motion of a sound source or motion of the listener, or both. A source of sound approaches and the observer hears a higher frequency. When the source moves away, the observer hears a lower frequency. This is like when you're at a stoplight and a fire truck comes by. In the distance, the siren has a lower pitch until it gets right up to you. The pitch continues to increase. It's at its very highest pitch or highest frequency sound right when that fire truck is next to you, and then as it proceeds to continue moving away from you, the pitch will decrease. The ear and hearing. The outer ear gathers and focuses sound into the middle ear, which receives and amplifies vibrations. The inner ear uses nerve endings to sense vibration and send signals to the brain. So your outer ear is called the pinna. Then you have the ear canal, which connects the outer ear and the inner ear together. And then you have your eardrum, which is where your ear canal dead ends. Your eardrum vibrates, and that vibration is transferred through those tiny bones in your middle ear, which are the hammer, anvil, and stirrup. And they are transferred into the cochlea, which is filled with little tiny hairs that sense the sound waves and convert it into electrical impulses that then move through your auditory nerves into your brain, and your brain can then make sense of what you're hearing. So how is sound reproduced? Sound is recorded by converting sound waves into electronic signals that can be produced and stored. Sound is reproduced by converting electronic signals back into sound waves. So this is how an old phonograph would work. This cylinder would rotate, and there's a little needle, and the needle moves up and down as there are ridges on the old cylinder. Cylinders were what they had before they had like LPs, the flat vinyl records that you're probably used to. Before that, it was a big cylinder. And as that needle moves up and down, it hits a little diaphragm, which is very similar to your eardrum. And then that diaphragm will amplify the sound as it moves through a horn, and that increases the volume so you can hear it. And we do have a phonograph in the pub room. Maybe I'll play it for you sometime. Music. Most musical instruments vary pitch by changing the frequency of standing waves. Resonance, which we already talked about, the response of a standing wave to another wave of the same frequency. So now you're going to watch video number 3 of good old Professor Dave, and he's going to explain standing waves and harmonics. And this again is an example of all of the different frequencies found on a piano keyboard, and a little formula triangle for if you needed to do the math about music or pitch. So let's talk about music for a few minutes. So first I wanted to show you guys this. This is a little more blown up version of what you had in your notes when it came to frequency and pitches. And I want you to particularly focus right in here in your fourth octave, which is what we'll be looking at in just a moment. So we have right here the frequency of each of these pitches. So this is middle C, or C4 in the fourth octave, and you can see the frequency of middle C when it's tuned exactly as 261.64 hertz. This note right here, which would be a C sharp if you're going up the scale, a D flat if you're going down the scale, is 277.18 hertz. And then obviously we keep moving up. D natural would be 293.66 hertz, and so on. Okay, how does this work? Well, if you look right here, this shows you intervals basically, and you can kind of tell how these line up. When your waves line up in a pleasing way like this, and there's like evenly divided, you get a nice harmonic sound. When the division is not even or equal, you get some dissonant sound, which we consider unpleasing in our culture. I also want you to notice something else. A right here, C is highlighted because this is middle C. A is highlighted because it's A440, and this is where orchestras tune. Exactly an octave below is 220. Exactly an octave above is 880. That's nice because there's no decimals there, and you can tell that those numbers are all exactly. You got doubled here, you got doubled here, and then when you move up, same thing is happening. Same thing for all these others. The math's a little more difficult because they're not nice round numbers like 440, but it's exactly what you've got going on here. 130.81 to 261.63. So we're basically doubling as we go up in each octave, okay? And then between the notes within an octave being C to C, D to D, E to E. The notes in between move up by definitely smaller intervals than being doubled. And I wanted to show you here, this would be a C major scale if you just played the white keys. It's a chromatic scale if you play the keys including the black notes or the half steps. There is actually a half step between E and F, which is why there is no black note here, and there is a half step, musically speaking, between B and C, B natural and C natural, which is why there is no black here. So if you're walking up a major scale and you're using only the white keys, you're naturally in a scale going to have a half step here and a half step here. I also want you to notice that your black notes have two names. That's because if you're going up, you read it as C, C sharp D, D sharp E, F, F sharp G, G sharp A sharp B, C. But if you're going down, it is C, B, B flat A flat G, G flat F, E, E flat D, D flat C. Okay, now we're going to listen to some pitches. C major, no sharps, no flats, all natural pitches. C4 or middle C. Go up one step, interval is now a second C, D. Together. A third C, E. Together. A fourth C, F. Together. A fifth C, G. Together. A sixth C, A. Together. A seventh C, B. Together. And a full octave C4 to C5. Together. C major scale with no sharps or flats. Chromatic scale with sharps and flats. C major scale with no sharps or flats. Chromatic scale with sharps and flats. You already heard that. So here it is again, slightly smaller than what we looked at before, and right here, this is the math, if you needed to do the math. So I'm wondering if any of you play instruments. Obviously, raising your hand won't do you any good when you're sitting at home. So here are our different families of instruments. Have a look, see if you see one that you play, or maybe one that you recognize. I know my instrument very well, but I've only ever seen it one time. And that was when I went here, when I needed the instrument recalibrated. That's my instrument. Not a very attractive picture, but those are my vocal cords. And when I needed my vocal cords recalibrated, like any other instrument, whether it be a scientific or musical instrument, this is where I went for help. If you look very closely, you'll see this little white spot right there. That's on my right cord, because this image is taken from above looking down my throat. And that is a lesion or a little scar tissue that I earned after having a really, really terrible bout with viral laryngitis, which is an inflammation of your vocal cords. And when I went there, the otolaryngologist asked me what problems I was having, and I told her I was having issues with my passaggio, which we'll discuss in just a minute. And she asked if there was a particular pitch that I could point to. And I said, well, my passaggio usually sits right around A natural, so I'm definitely having some issues there. So she had me, she pointed this little camera down my throat like that. That's a still image from the video there. And she had me sing sirens, just kind of like, ooh, ooh, up and down, up and down. And there was an oscilloscope that was also reading the frequency of the sound I was producing, and those images were showing up on a screen. And it should make like a nice arc up and down on a graph, but there was a little bump in it. And when she zoomed in, that bump was at 442 hertz, and A natural is at 440 hertz. So when you know your instrument well, you know your instrument well. So this is weird but cool. You're going to go watch video number 4, which is a close-up of vocal cords while singing, which is what I saw on screen when the otolaryngologist had me in there. It was pretty fascinating. Okay, we're going to watch a couple of videos here on the physics of music, musicality in particular, and we're discussing vocal music in particular here. But there's going to be some terminology used, and I wanted to give you an idea of what's going on so you're not completely in the dark. So intervals are what I played for you a little bit ago on the keyboard. That's a number of steps between notes. So like if you remember, I said C to D is a second, C to E is a third. In one of these videos, a fifth will be discussed, and a fifth, for example, is like C to G. Vocal pitch is the pitch produced by tightening and loosening of a singer's vocal cords. Passaggio. Okay, this is what I was having issue with when I went to the doctor. It's also known as break tone. The pitch above which a singer can only sing higher pitches using head voice. Okay, so we're going to discuss resonance in just a moment here. So if your passaggio is a little collection of notes right in your mid-range for a singer, and above those notes you can only resonate sound in your head. Below those notes you can resonate sound in your chest or frontal or pseudo resonance. And those particular notes that are in your passaggio you can do in all of those ranges. So you can do them in chest, pseudo, frontal, and head, but often what you use is called mixture, which we'll talk about in just a second here. So vocal resonance, singers use different parts of their anatomy to best resonate different pitches. Chest voice is where your pitch is resonated predominantly in a singer's chest. For lower notes, it's not really a thing for higher notes, and you can think of the sound as dark. If you've ever heard like a male opera singer, like a bass with a deep voice, this is kind of a great example of chest voice. Pseudo resonance is where your pitch is resonated primarily in your frontal resonance, but with a little touch of chest. And it's often used to add character to mid-range and lower notes, and you can think of it as kind of a thick sound. Your frontal voice is where your pitches resonated in between your head and your chest, and you can think of it as right in a singer's mouth. It's mostly for low to mid-range pitches, and you can think of it as bright. Often you'll hear voice instructors use the visualization of send the sound right to the back of your top teeth. You may hear somebody say that if you do chorus or, solo work. Now here's where mixture comes in. This is a blend of frontal and head. It's often used to cover those passaggio notes, which are the notes that sit on your break tone, and it's probably the most challenging resonance to master. It can be very difficult for people. And you can think of it as a spread sound, and it's the kind of thing where you really have to think about where you are aiming your note, where your placement. Singers will refer to it as placement. Where am I placing that note? Where am I resonating it? And lastly is head, and this is the pitch that is resonated predominantly in the singer's head or sinuses, and it can be used for low notes, but it is required for high notes above the passaggio, and you can think of it as a very light sound. This is typically most often what you'll hear in choral singing. Now, there's also something called a belt voice, and you've probably heard of this, and this is when a singer uses his or her frontal resonance on notes leading to or within the passaggio. And what happens here is it's largely produced by bouncing the sound off the hard palate in the singer's mouth. But because those notes are the highest frequency notes that a singer can produce using frontal, they tend to come out really loud. And so if you've mastered a belt voice, then that's what you get. And this is typical of like Broadway singers. Back phrasing. Back phrasing will be discussed in one of these videos. This is when a singer or an instrumentalist will place a note slightly behind the beat, and this is for artistic effect. Triplets. Triplets are when 3 notes are played or sung within a span of 2 beats. So the way you do a triplet, if you're trying to hear it, is you would clap a steady beat and say cup of tea. So if my beat is 1, 2, 3, 4, but I want to fit 3 notes in between the claps, it becomes 1, 2, 3, 4, cup of tea. So cup of tea, all 3 of those words came within 2 beats. So there are some triplets in one of these examples we're going to be hearing. Vibrato, this is when a musician or vocalist intentionally causes a minor repetitive fluctuation in pitch. Violinists will do this by wiggling a finger on a string. The opposite of vibrato is straight tone, in which there is no fluctuation in pitch. Modulation is a change in key signature. So key signature is denoted by the placement of sharps and flats within a given scale. We were doing C major earlier when I was showing you pitches. It gets a bit complicated, but in general, there are 15 major and 15 minor key signatures in Western music. I should say key signatures, but you'll live. So there will be modulation discussed in one of these videos. So now I want you to watch video number 5. Video number 5 features Seth Rudetsky, and he is deconstructing the song He Plays the Violin from the musical 1776. Seth Rudetsky is a character. He is one of the DJs on Sirius XM Broadway channel. He is very well known within the New York music theater scene. He is a composer and a conductor, obviously a DJ. He kind of knows everybody there is to know, and he's entertaining. But note that this song is being performed by Betty Buckley, and the he that she is discussing in the musical 1776 is Thomas Jefferson, who was a violinist. She is Thomas Jefferson's wife in this musical. So go ahead and watch Seth. And next, we're going to watch a video here on this gentleman's opinion of how autotune destroyed modern music. So now that you've just seen Seth Rudetsky give a serious breakdown of the musicality of a vocal production of a particular number, a particular song, that he broke it down into tiny, tiny bits and talked about all the artistic stuff that was put in with all of the physics to make it music and not just sound. Now watch this bit on autotune. And lastly here, what does music have to do with science? Well, science is deeply ingrained in many aspects of the arts, especially music. This becomes clear when looking at music through the lens of STEM education. Music connects language, math, time, history, religion and faith, and multiple branches of science, physics, chemistry, and biology. Certain parts of your brain perform certain tasks and retain certain information, and music has the ability to connect those areas. So this graphic image here on the left, this is a musician, and this is the musician's brain listening to music on the left, and on the right, that is the musician playing his or her instrument. You can see how lit up that brain is. Now, regions of the brain do particular tasks, and when you're playing an instrument or singing and reading music, your whole brain will light up like that, and that is because it connects various areas of your brain. And there are very few other things that do that. So I want you to watch video number 7 on how using music can help unlock Alzheimer's patients' memories. And lastly, I want you to, if you can in your life, learn music. It's for your own good. After seeing that Alzheimer's patient, I hope you realize why. Have a great week. Lab is excused. I will see you back next week.